Hello everyone, this is Physics 103. This lesson is on atomic structure. So we will be discussing a particle in a three-dimensional infinite potential and its energy degeneracies. So solving the Schrödinger equation for a particle in a 3D infinite well, we have this wave function psi of xyz, wherein it is defined by a normalized constant 2 over L raised to the 3 halves times 3 sinusoidal functions which represent stationary states along x, y, and z. So this wave function is also defined by 3 quantum numbers nx, ny, and z, which range from 1, 2, 3, and so on. So this wave function has its allowed energy levels, which is given by E equals this constant pi squared h bar squared all over 2m multiplied by this term, which is dependent on the dimension Lx, Ly, and Nz, and Nx, Ny, and Nz. So now we ask, what will happen to our particle if we are to confine it in a symmetrical potential? For example, a box. So creating a box, we reduce our dimensions on Lx, Ly, and Lz to be equal to just L. So we have a box, an infinite potential box with dimension with a side of L. Okay, so our energy levels will reduce to this equation wherein we can factor out L from these terms, and we see that the energies now are purely dependent on the quantum numbers nx, ny, and nz. So in doing so, we can see that different quantum states, which are defined by nx, ny, and nz, will have same amounts of energy. So different quantum states will be energy degenerate. So we know that a specific set of quantum numbers determine a specific quantum state. But confining a particle in a symmetric potential, we will have energy degeneracies. So for example, we have these three different quantum states, 211, 121, and 112. So we will see that if we calculate their energy levels, these three quantum states will have the same energies. So let's try for quantum state 211. So we have h bar squared pi squared over 2 ml squared times the sum of the squares of their quantum numbers. So we have 2 squared plus 1 squared plus another 1 square. Now this is 4 plus 1 plus 1, so 6 in the numerator divided by 2. We would have 3 h bar squared pi squared over 2 ml squared. So this is the specific energy for this quantum state. Now let's try to find out the energy for quantum state 121. So energy 121, we have the same constant for 2 ml squared. So times quantum numbers, 1 squared plus 2 squared plus 1 squared, and we see that we arrive at the same energy value. So 3 h bar squared pi squared over 2m L squared. So we can do the same for E112, and we will find that its energy level is still 3 h bar squared pi squared over 2ml squared. Okay, so these are three different quantum states, but their energy levels are all the same. So here you can see the probability distribution, or psi squared, of these three quantum states. So we have quantum state 211 here. Sorry, this should be 121. We have 211 and quantum state 121 and quantum state 112. Okay, so this is a plot of the energy levels for different quantum states. So for our ground state, we have only one quantum state associated to it. We have quantum state 111. So this is our ground state. So above the ground state, we have three quantum states associated with the same energy. So these quantum states are the ones we previously solved: 211, 121, and 112. So we say that these three quantum states are three-fold degenerate. Okay, moving up another energy level, we have another three-fold degenerate quantum state: 221, 212, and 122. And again, moving up, we have another three-fold degenerate. And once we reach quantum state 222, we see that there is no degeneracy. Or we say it's non-degenerate, like the ground state. Okay, above quantum state 222, we have 6 quantum states that have the same energy. So we say that this is 6-fold degenerate. Okay, and we can move up and up the energy levels. So what's important to learn in this lesson is that symmetries from potentials always give rise to degeneracies in energies. Degeneracies in the energies